In this very short video, we will introduce the Poisson distribution. So your book has chosen not to cover the Poisson distribution in detail, but to give you a little sense of what it is. So the Poisson distribution measures the number of events, a large population over a unit of time. For example, the number of lightning strikes in a day, or number of people getting married in a year, or maybe it's the number of earthquakes in a year. So the probability of observing K events, and you're given some unit of time. So it could be a day, it could be a year, it could be an hour, it could be a second. So the probability of observing K events in this unit of time is lambda to the K, where lambda is the average number of occurrences per unit of time. This E is a mathematical constant whose value is equal to approximately equal to 2.718. E is kind of like pi in that it has some infinite number of decimals, and we don't write out the decimals. Like usually we don't say 3.14159, we say pi. So in this case, we say E, and it's 2.718. This E is also closely tied to logarithms. So now our formula is lambda raised to the K times E raised to the minus lambda divided by K factorial. The conditions where we're looking whether a random variable is a Poisson distribution, one, we're looking for the number of events, again, where the probability that K events occur in a period of time. The population that generates such an event is large, and the events occur independently of each other. Here we have a histogram showing the number of occurrences of AMI, I think that's a type of heart attack, on 365 days for New York City. The sample mean, which is somewhere around here, 4.38, is similar to the historic average of 4.4. The sample standard deviation is about 2, and the histogram indicates that about 70% of the data fall between 2.4 somewhere here and 6.4 somewhere here. The distribution shape is unimodal and skewed to the right as it trails off to the right. Let's set this example up so we can calculate an event. So we're going to say this is a Poisson random variable. So X then is the number of AMI visits per day. This is our random variable, which is a Poisson variable. And our time interval here is 1 day. And so our lambda, our average number of visits, that's given to us here, the historical average of 4.4. So that's going to be our lambda, and this is per day. Again, this is our unit of time. Now, if we want to calculate, for example, probability x equals 3, that our random variable equals 3, in other words, there's 3 visits in any given day, then we set k equal to 3. Again, lambda is 4.4. So probability k equals 3, using our formula here, lambda is 4.4 raised to the k, which is 3. Our e to the minus lambda, so 2.718 to the minus 4.4 divided by k factorial, which is 3 factorial, and we have a probability of 17.4%. I would like to do one more example for you. So website hosting companies use the Poisson distribution to model the number of expected visitors per hour that a website will receive. So suppose we have a given website, it receives an average of 100 visitors per hour. Find the probability that the website receives 120 visits in an hour. So our random variable x is the number of websites visits per hour. And this we're going to assume is a Poisson distribution. So our average, our lambda, is going to be 100 visits per hour. And if we want the probability that x is equal to 20, then k is equal to 120. We plug it into our formula. So that's lambda to the k, that's our 100 to the k, which is 120, times our e to the minus lambda, so that's 2.718 raised to the minus 100, divided by k factorial, so that will be 120 factorial. And that's equal to 0.56%. So that's actually a very small probability. Anyway, so that's it for this video. Thank you for watching.